in continuing with the properties of group 17 elements. In earlier class or video, we have discussed the reactivity order of group 17 elements. There we have explained fluorine is the most reactive and iodine is the least reactive, and we have also explained the reason behind this. So let's discuss some reactions, general reactions of halogens, and then we'll come to some specific compounds of halogens and their properties and their chemical properties, etc. So coming to the chemical reactions, of halogens. So first चलते a reaction with water. तो ये halogens react with water when this gives you HX plus HOX. This reaction is given by when X is equals to Cr or X is equals to bromine. Iodine and fluorine does not give this type of reaction, whereas fluorine reacts with water to give you HF on oxygen. Sometimes this fluorine also reacts with water to give you HF and ozone. So look at this, you have balanced this reaction. So fluorine reacts with water to give you HF and oxygen, or fluorine reacts with water to give you HF and ozone. Whereas with I reacts with to give you HI and HOI. This reaction is not spontaneous in forward reaction, but this is spontaneous in reverse reaction. So this is how halogens reacts with water. So in previous class we have discussed these halogens being non-polar, their solubility in polar compound, a polar solvent, is very less. However, these chlorine, bromine and fluorine may react with water to give you some sort of products. Now coming to next reaction, these halogens reacts with hydrogen gas, and this gives you HX. This HX, the anhydrous is known as hydrogen halide anhydrous. Anhydrous is known as hydrogen halide, and hydrated solution is known as hydrohalic acid. Hydrated solution. So HX is known as hydrogen halide if it is anhydrous, or if this HX is dissolved in water, that is hydrated solution. So hydrated solution is known as hydrohalic acids. And these, if you look at this, the reaction is fast if halogen becomes fluorine, slow if hydrogen X becomes iodine. That is the reactivity order. So all halogens react with water to give you HX, hydrogen halide. These halogens also react with phosphorus. So look at this. H2 reacts with phosphorus. This gives you PX3, phosphorus trihalide, and phosphorus pentahalide. This trihalide is given by all halogens: fluorine, chlorine, bromine, iodine. Whereas pentahalide is given by fluorine, chlorine, and bromine. Iodine does not react with phosphorus to give you phosphorus pentaiodide, whereas fluorine, chlorine, and bromine reacts with halogen to give you pentahalide. So the reaction of halogens with phosphorus gives you two types of compound, that is phosphorus trihalide or phosphorus pentahalide. Number 4, these halogens reacts with this hydrogen sulfide. So halogens being a very good oxidizing agent, these oxidize sulfide ion, that is -2, to sulfur. So all halogens has a very good affinity for this hydrogen sulfide. All halogens oxidize hydrogen sulfide or sulfide ion to sulfur, -2 to 0. All halogens. So this is how hydrogen sulfide reacts with halogens. These halogens also reacts with sulfur. The reaction of halogens with sulfur. So halogen reacts with sulfur to give you H2X2. This is given by when X is equals to Cl. So chlorine reacts with sulfur to give you H2Cl2, whereas this reacts with sulfur and this gives you SH6, whereas X is equals to fluorine. So fluorine reacts with sulfur to give you sulfur hexafluoride. This is the reaction of halogens with sulfur. Halogens X2 also reacts with carbon monoxide gas to give you COX2, carbonyl halide, where X is equals to Cl and Br. So reaction of halogens with carbon monoxide to give you COX2, where X is your chlorine or bromine, that is carbonyl halides. Then coming to next, these halogens also reacts with sulfur dioxide gas to give you SO2X2, where X is equals to Cl and F. This is sulfonyl chloride. Fluorine and chlorine reacts with sulfur dioxide to give you SO2 and Cl2. X2 also reacts with ammonia gas. If ammonia gas is taken in excess, ammonia gas taken in excess, when this gives you ammonium halide and nitrogen gas. Here X is chlorine. So chlorine reacts with ammonia gas. Ammonia gas taken in excess, when this gives you nitrogen gas and ammonium chloride. But if X2 gas, X2 is taken in excess, reacts with ammonia gas, then this gives you an X3 plus HX, again X is equals to Cl. To chlorine reacts with ammonia gas. If chlorine gas is taken in excess quantity, this gives you NCl, trichloroamine plus hydrogen halide. So look at this, there is a difference of product. If ammonia gas is taken in excess, nitrogen gas is formed. If chlorine gas is taken in excess, this gives you NCl3. Next, these halogens also reacts with sodium hydroxide or alkali. If this is cold and dilute, then this gives you NaX plus NaOX plus H2O. So where this X is chlorine and bromine. So chlorine and bromine dissolves or reacts with sodium hydroxide, when this gives sodium hypohalide and sodium halide. But if sodium hydroxide or alkali, any alkali, potassium hydroxide or any alkali, if this alkali is hot and concentrated solution, then the product is halide ion and chlorex ion, OX. Halide ion. So look at this, with cold and dilute solution, OX minus is formed, hypohalide ion. With hot and concentrated solution, halide ion is formed. So depending on the concentration or coldness or hotness, this reacts to give you different types of product. And here this X is chlorine, bromine and iodine reacts this to give you this product. So there are different types of reaction that is given by halogens. Some more reaction I am giving here. Halogens also reacts with another halogen to give you inter-halogen compounds. Suppose this reacts with X2 plus X prime, when this gives you a mixture of inter-halogens, XX prime while this X prime is halogen which is more electronegative than X. These compounds from here, these are known as Inter-halogens. So compounds formed between halogens is known as inter-halogens. So in this way, these halogens gives you different types of reaction. Apart from this reaction, we have seen a number of reactions in which this is used for halogenation of hydrocarbons. So hydrocarbons react with halogen to give you haloalkanes. That is entirely different thing that we often discuss in organic chemistry. But if you look at this inorganic substance, these halogens shows different types of reaction. Now, one of the most important property of this halogen is these halogens are showing a powerful oxidizing property, and we have discussed what is the order of oxidizing character of halogens. Fluorine being the most electronegative is the strongest oxidizing agent, and iodine being the least oxidizing agent. And when these halogens acts as an oxidizing agent, the halide ions shows powerful reducing agent. So in case of reducing agent, Hi, I minus is the strongest reducing agent and F minus is the least reducing agent. Now come to some important compounds of halogens. Some important compounds of halogens. Firstly, chlorine gas. So firstly, preparation. Preparation of chlorine gas. Now we have looked at this MnO2, manganese dioxide. These reacts with HCl when this gives you MnCl2, Cl2 gas plus H2O. Or instead of this, we can also take this combination MnO2 reacts with a mixture of sodium chloride and sulfuric acid. So these force NaCl or KCl reacts with sulfuric acid to force this gives you HCl and Na2SO4. So these HCl further reacts with MnO2 to give you the same product. So that is MnCl2 plus Cl2 gas plus H2O plus sodium sulfate. So this is laboratory method for preparation of chlorine gas. Now, from synthesis point of view, we have a process. This is known as Decons process. It's used for commercial production of chlorine. In Decons process, this hydrogen chloride HCl is oxidized with atmospheric oxygen in presence of catalyst COCl2. So oxidation of HCl with air means aerial oxidation, means oxidation in presence of oxygen gas in presence of catalyst. When this gives you H2O and the Cl gas is formed. So commercially in large scale chlorine gas is produced by this Decons process. Another method is electrolysis. Electrolysis of brine solution. That means aqueous sodium chloride. Or we can take simply NaCl. So simply say electrolysis of NaCl. So look at this, we have this NaCl solid. You heat this, at this melting point this gives you sodium and Cl minus. Now this undergoes electrolysis. So anode, there is oxidation, so Cl minus is oxidized to chlorine gas, an electron is released, and at cathode, this Na plus takes up this electron and is converted into sodium. So look at this, when we electrolyze fused NaCl, there is a production of chlorine gas at anode and sodium at cathode. Or this chlorine gas is produced as a byproduct of many of this electrolysis process. So this is for large scale production of chlorine gas. Now this chlorine gas are given in the various types of reactions given by halogens. There I have shown you which particular halogen reacts with which particular substance. Now I am giving you some specific properties of this chlorine gas. Aqueous chlorine or hydrated chlorine gas is a powerful oxidizing agent, as a bleaching agent. So look at this. Let's see why chlorine, aqueous chlorine, is a powerful bleaching agent. The reason is chlorine gas, when dissolved in water, this gives you HCl and HOCl, hypochlorous acid. These HOCl being unstable, these decompose to give you HCl, and active or nascent oxygen is formed. These nascent oxygen, being a very strong powerful oxidizing agent, shows bleaching property. Bleaching action. So look at this. The bleaching action of aqueous chlorine gas is due to the formation of this nascent oxygen. So the chemical reaction is, in the first step, chlorine gas reacts with water to give you HCl and HOCl, hypochlorous acid. This hypochlorous acid being unstable decomposes to give you HCl and the bleach, this nascent oxygen or active oxygen. This active oxygen, being a very powerful oxidizing agent, acts as a bleaching action. So the bleaching action of chlorine aqueous solution is due to the formation of this active oxygen or nascent oxygen. Now this chlorine is used for preparation of organic compounds in drugs. Drugs etc. like CCl4, look at this, carbon tetrachloride, chloroform, like DDT, dichloro, diphenyl, trichloro, freons, which is used in the refrigerations. So these types of many organic compounds and important drugs, in this preparation we use this chlorine gas. This chlorine gas is also used for preparation of some poisonous gas. Poisonous gas, preparation of some poisonous gas like COCl2, which is known as phosgene, and then CCl3NO2, nitrochloromethane. This compound is known as tear gas. This is often used to control, used by police to control the crowd. That is tear gas. Then we have look at this Cl, CH2, CH2 sulfur, CH2, CH2, Cl. This is known as mustard gas. So these types of important poisonous gas which is used in chemical warfare is also prepared from chlorine. So this is some of the important uses of this chlorine. Now chlorine is also used for sterilizing the drinking water, that this often marketed as chlorine tablets. This is the reaction. So when chlorine is dropped in water, this gives you HCl and SOCl. HOCl decomposed to give you nitrogen oxygen, and this is acting as a powerful oxidizing agent. This kills the microbes and germs present in the drinking water. Now reaction of this chlorine with dried slaked lime, that is calcium hydroxide, these gives you a very important compound that is known as bleaching powder. Now bleaching powder is often written as CaOCl2 calcium oxychloride, but actual composition is CaOCl2 calcium chloride this is the actual composition of bleaching powder, but the bleaching action is mainly because of this. So this is often written as bleaching powder CaOCl2 calcium oxychloride. So if you are asked to write down the actual composition of bleaching powder, then you have to show. If nothing is mentioned, then this will be sufficient. That is calcium oxychloride. In this calcium oxychloride, look at this. We have two different types of chlorine. One is attached to oxygen. The one attached to oxygen, this is having +1 oxidation state. The one which is directly bonded to chlorine as calcium, this is -1. So we have two different chlorine. One is -1, one is +1. The average oxidation state will be 0. Calcium is +2, oxygen is -2. So this is the oxidation states of chlorine in bleaching powder calcium oxychloride. This chlorine is also used for chlorination of hydrocarbons. So look at it, take this. CH4 reacts with chlorine gas in presence of sunlight. When this gives you a mixture of halo compounds CH3Cl, CH2Cl2, CHCl3 plus CCl4. A mixture of halogen substituted compounds will be formed. Similarly, if you take this alkenes, these also reacts with chlorine in presence of CCl4, that is a medium. When this gives you addition compounds. So this chlorine is used for chlorination of hydrocarbons. This may be alkene, this may be alkyne, or this may be alkanes. So we can take this reacts with chlorine, this gives you addition compound. So this is some of the reactions of chlorine, and one reaction I have given you earlier, that is chlorine plus NH3, this gives you N2 plus NH4Cl, तो if ये तब बनेगा if NH is excess, but if chlorine is taken in excess, then with the same reacting mixtures chlorine gas taken in excess, ammonia in limited quantity, then this gives you NCl3 plus HCl. So this is the difference in product. So with excess of ammonia, nitrogen gas is formed. With excess of chlorine, NCl3 is formed. So this is some of the important uses of chlorine and its some important chemical reactions given by chlorine. Now coming to the second compound, that is hydrohalic acids, HX. As I told you, anhydrous compound is known as hydrogen halide, and hydrated solution is known as hydrohalic acids. So hydrohalic acids means aqueous solution of HX is known as hydrohalic acids. So look at this. We have different types of HX, that is HF, HCl, HBr, HI. Now if you look at this, moving from HF to HI, the size difference between halogen and hydrogen increases. As the size difference increases, the bonding strength decreases or the bond length increases. All these are covalently bonded molecule. Bond distance increases from HF to HCl to HBr to HI. If the bond distance increases, bond strength will decrease. Bond strength. So the strongest bond is HF, weakest is HI. Now as the bond strength increases, stability will decrease. So HF is the most stable and HI is the least stable. Now as the bond distance increases, bond strength decreases, tendency to the break bond increases. Now based on this, we say the acidic strength of this HX increases from HF to HCl to HI. So in aqueous solution, HI is the strongest acid and HF is the weakest acid. Now the question here is, fluorine being the most electronegative, the polarization of bond is maximum in case of HF, so HF should have been the strongest acid. But hydrogen being attached to fluorine, this hydrogen is stabilized by hydrogen bond. So look at this. We have this HF, polarization of the bond. This reacts with another HF. Look at this. So this hydrogen, which is attached to electronegative atom fluorine, is sandwiched between two electronegative atoms, and this hydrogen is stabilized by intermolecular hydrogen bond. So as hydrogen is stabilized by intermolecular hydrogen bond, tendency to break this hydrogen decreases. As a result, the acidic strength is minimized. So this should have been the strongest acid, but this becomes the weakest acid because of this phenomenon. Hydrogen bond. Whereas hydrogen bond is not present in the rest of the compounds. So in the rest of the compounds, bond length increases, tendency to break the bond increases. As a result, acidic strength increases. So as the acidic strength increases, then Ka, acid ionization constant, will also increase. As the Ka increase, then pKa, negative logarithm of Ka, will decrease. So Ka and pKa both are having inverse relationship. If pKa is more, acidic strength is less. If pKa value is less, acidic strength will be more. So this is variation in properties of. Now, as I told you earlier, halide ions are very powerful reducing agents. So as a reducing agent, of I minus is the strongest. So I minus is the strongest reducing agent, whereas F minus does not show any reducing property. Fluorine being the strongest oxidizing agent, F minus is the weakest reducing agent. I2 being the least oxidizing agent, I minus becomes the strongest or the most powerful reducing agent. So this is HX. So this is a comparison in the properties of different hydrohalic acid, that is aqueous solution of HX. Now after this, let's go to Oxoaccess of Halogens. Oxoaccess of Halogens. Hydrogen forms different types of oxoacids. Oxoaccess means the acidic hydrogen is bonded to oxygen. That is oxoacids. So we have this fluorine, bromine and iodine. These forms different types of oxoacids. First one is HOX, HXO2, HXO3, HXO4. These XOX, this is formed by all these halogens, HOF, HOCl, HOBr, HOI. HXO2 is formed by chlorine only, HClO2. This is not given by fluorine, bromine and iodine. HXO3 is given by Cl, given by bromine, given by iodine. Fluorine does not form HXO3. HXO4, fluorine does not form HXO4. Chlorine, bromine and iodine forms this series of acid, HBrO4, HiO4. So these are the various oxoacids formed by these halogens. Fluorine forms only one oxoacid, that is HOX. The reason being, fluorine being the most electronegative, smallest inside, does not have any d orbital, so fluorine forms only one haloacid, that is oxoacid, that is HOF, whereas the rest of the elements, chlorine, bromine and iodine, contains vacant d orbital. As a result of this, these forms other oxoacids. Let me give you the names of these acids also. So if you look at this, the oxidation states of this halogen in all these acids. In this is +7 oxidation, halogen is in +7 oxidation state. This halogen is in +5 oxidation state. This is in +3 oxidation state. This is in +1 oxidation state. Now this acid are known as, if you look at its name of these acids, standard name is acid. This is Halide-2 acid. This is written as Halide-3 acid. This is written as Halide. This is 3. This is 5. Halide-7 acid. Common name, this is standard name. Common name, this is hypohalous acid. Hypoiodous, hypobromous, hypochlorous, hypofluorous acid. This is halous acid, chlorous acid. This is simply known as halic acid. Chloric acid, bromic acid, iodic acid. This is known as perhalic acids. Perchloric, perbromic, periodic acids. Now these are the names of these standard name as well as the common name of these different types of oxoacids. Now these acids, as I told you, these are known as oxoacids. So hydrogen is attached to the oxygen atom. So this is formulated as HOX. This is HOXO. So this acidic hydrogen is attached to oxygen. This is HOXO2 HOXO3. Now if you look at this, in this oxygen and halogen bond, this is multiple bonds. So we have look at this HOX double bond O. This is so this is how these acids are visualized. So this is acidic hydrogen which is attached to oxygen, acidic hydrogen which is bonded to oxygen, acidic hydrogen which is bonded to acid. So if you look at this, all these acids, the N factor, number of ionizable acidic hydrogen is 1. If you look at this, hybridization, of halogen, all this is sp3, and all these oxoacids of halogen, central atom halogen is sp3 hybridized. So that means this is tetrahedral. So if you look at the structure, so we have this X O H. We have look at this X So these are the rest of the position is we are having a lone pair electron here. So this is perfect tetrahedral. This is something like what a pyramidal type shape of ammonia. This is something angular. This is linear. So these are the various oxoacids. Now look at this. These higher halogens form oxoacids in higher oxidation state. In all these oxoanions, the oxygen is stabilized by p pi d pi bond. This bond formed here, this is known as d pi p pi. Fluorine does not have, as I told you, does not have vacant d orbitals of fluorine. This oxoanion cannot be stabilized by p pi d pi type bond. So oxygen has got electron in filled p orbital. Halogen has got vacant d orbital. So there is a transfer of electron density from filled p orbital of oxygen to the vacant d orbital of halogen. As a result, this oxoanion is stabilized by p pi d pi or d pi p pi type back bonded. That means electrons coming from filled p orbital of oxygen to the vacant d orbital of halogen. So as a result of this oxoanion being stabilized, these higher members chlorine, bromine, iodine forms these three oxygen. Now if you look at this, the acidic character of this, moving from this left to right in any particular series, look at this, take this series HOI, HXO2, XO3, XO4. So moving from left to right, this series, as the oxidation state of halogen increases or as the percentage of oxygen increases, acidic character increases. So this is acidic character. Acidic strength. So moving in any particular series, moving from this HOX to HXO4 means as a percentage of oxygen increases or at the oxidation state of central atom halogen increases, acidic character increases. Take any particular series, HOX or HXO3 series or HXO4 series. Moving from any particular series, moving from fluorine to iodine, moving from this to this, as the electronegativity of central atom decreases, acidic character decreases. So in case of HSO4, strongest acid is HClO4 and the weakest acid is HiO4. That means in any particular series, as the electronegativity of halogen decreases or as the size of halogen increases, the acidic character decreases. In a series of oxoacids in which halogens are in different oxidation state, as the oxidation state of halogen increases for a particular halogen, acidic strength increases. These oxoacids are very powerful oxidizing agent and these acts as an oxidizing agent. So in case of acting as an oxidizing property, the oxidizing agent character decreases. So as an oxidizing agent, HOX is the most powerful oxidizing agent and HXO4 is the least powerful oxidizing agent. So these are the various properties of this oxoacids of halogen. I have given you hybridization, shape, structure. Then we have oxidizing character, acidic strength, oxidation state, then common name and standard name. These are the oxoacids of halogens. So these are some of the important properties or compounds of halogens. And one more important thing that is left is inter-halogen compounds. So should I write this? Yes. So let's go to inter-halogens. So next we are going to discuss inter-halogens. Means means compounds formed between two different halogens, that is known as inter-halogens. As I told you, from preparation of point of view, we have this X2 combines with X2 prime, this gives you X prime. We have look at this combines to give you X prime 3, this may also give X prime 5, X prime. So examples, look at this, we can have IFClF, Br, FICl, etc. X3 prime, example BrF3, ICl3, etc. X5, IF5, BrF5, etc. X prime 7, the only example is IF7. Now let's discuss the structure of this. X prime type. So if you look at this, X prime is more electronegative, X is less electronegative. So the central atom is less electronegative, this is central atom. So therefore look at this, electron pairs present in the valency shell of this central atom, that is 7. Number of other atom is 1 divided by 2, so we have 4 electron pairs. So since number of other atoms is 1, so we have 1 bonded pair and the remaining is 3 bonded pair. Now since the number of electron pair is 4, so we require 4 hybrid orbitals, so the hybridization is sp3. So look at this, we have this X, this is X prime. So geometry is tetrahedral, but the shape is linear shape. Linear shape, but the geometry is tetrahedral here. So this is the structure and geometry of X prime. Now coming to X prime 3, I can look at this. X is our central atom. So let's find out electron pairs. We have 7 plus 3 by 2, so we have 5 electron pairs. Number of other atoms is 3, so we have 3 bonded pairs and 2 lone pair. Since the number of electron pair is 5, we require 5 hybrid orbitals, so the hybridization is sp3d and the geometry will be trigonal bipyramidal, but the shape will be something different due to the presence of this lone pair electron. So in trigonal bipyramidal geometry, the lone pair occupies equatorial position. So we have look at this is X. So we have this X prime, we have this X prime, we have X prime, and these two equatorial position is occupied by lone pair. Because of this, this shape is T shape. This is something like T shape. So if exclude this lone pair, we are getting this T shape. Now coming to X prime 5, again X is central atom, so electron pairs is 7 plus 5 by 2, so we have 6 electron pairs. Number of other atom is 5, so we have 5 bonded pair and 1 lone pair. So since total electron pair is 6, so we require 6 hybrid orbitals, so the hybridization is sp2d2. So geometry will be octahedral, but the shape will be something different from this octahedral because of this lone pair. So if you look at this, it is X 1 one position is occupied by lone pair, remaining is occupied by X prime. So this structure is known as square pyramidal. Square pyramidal. Then we have X prime 7. The only example is IF7 as I have given you. You can look at this is central atom. So electron pairs is 7 plus 7 by 2, that is 7. So we have 7 bonded pair and 0 lone pair. So 7 hybrid orbital is required. So the hybridization is sp3 d3 type, and the shape is pentagonal by pyramidal. So we have a regular pentagon, center is occupied by this X, then we have this. It is X prime, X prime, X prime. That is pentagonal by pyramidal. So these are inter-halogens. Now these inter-halogens are more reactive than corresponding halogens. The reason being, all inter-halogens are more reactive than the corresponding halogen from which it is being prepared. The reason is due to the less polarization of this bond. The polarity in this bond is less, or because of less electronegativity difference, this X prime bond is less polar and is more reactive than X2 or X2 prime. Now as the electronegativity difference increases, the stability of these inter-halogens also increases. So when we compare the stability of this inter-halogen, we have to see the electronegativity difference. As the electronegativity difference increases, stability of these inter-halogens also increases. So keep in mind, all these inter-halogens are more reactive than the corresponding halogens from which it is being prepared. The reason being due to less polarization of this X prime bond due to less electronegativity difference. So this is a brief discussion about some important compounds and chemical properties of halogens. So with this, we'll conclude this halogen family, and next we'll move on to noble gas family. Thank you.